Assalamualaikum and good morning. I'm back to Sir Halim, our lecturer for Systemic Data Imaging for this semester. And my name is Haikal Halimi. And for today's agenda, I will present to you about wave equation migration. So for the outline of this presentation, it goes from abstract introduction, and I will explain about the comparison between the wave equation migration and the Kirchhoff migration. And later, I will proceed with the wave equation migration that divided into two, which is a one-way migration and two-way migration. And deeper, we will goes into the case study of this topic, and finally about the recent discoveries on this topic. So a standard stack seismic section merely shows the data as passing wave field collected at certain places on the Earth's surface, and this may bear a little resemblance to a cross section of subsurface reflectors in areas of complex geology. And basically, the method of migration is used to convert the seismic section wave field into a reflectivity display. As a result, every seismic migration technique should be able to be linked to a solution of the scalar wave equation, the presumed mathematical description of wave propagation in the Earth's subsurface. So, given a suitable precise velocity model, a pre-stack depth migration offers a structural representation of the subsurface by transferring seismic data from the time domain to depth domain. And basically, the wave equation migration can be divided into two subsections, which is a one-way and two-way. And during the last decade, the finite difference migration based on a one-way approximation to the wave equation has gained a popularity. And as mentioned by operator in 2000, when multipathing occurs, such as around salt bodies, it is widely assumed that the outcome of one-way equation migration is preferably than a ray-based migration. And Albertine in 2002 also mentioned that the ray-based migration, on the other hand, offers a more accurate pictures of a steep slopes. And the full two-way wave equation more accurately describe the wave propagation in a complex media. So this is the comparison between the wave equation migration and the Kirchhoff migration. In terms of cost, wave equation migration is high cost, particularly in 3D stack imaging, compared to Kirchhoff migration. But in 2D, they both are approximately the same cost. So in terms of the complex model, with equation migration naturally handle multipathing of the reflected energy because the solution of the wave equation is not computed as a finite set of the high frequency arrival, but the whole wave field is propagated at each step of the wave field continuation process. And for the Kirchhoff migration in handling the complex model, it causes a multipathing in the propagating wave field, and the integration surfaces are multivalued. And the numerical estimation of these multivalued surfaces and the numerical integration of the data over them can be cumbersome and prone to errors. So the image below is the comparison obtained by Papenholz in 2001, and is the comparison between the image obtained by the Kirchhoff migration applied to the synthetic dataset model over the salt body body, and the image obtained by on the right side is the image obtained by the wave equation migration method from the same data. Uh, for the one-way wave equation migration, since the two-way operator has a large computational cost, particularly in three dimensions, a one-way wave equation was introduced, and a two-way wave equation can be approximated by an outgoing and downgoing operator, assuming a constant density. The one-way operator into dimension is based on the formula below, with z as the marching direction. One-way equation also less cost consuming compared to the two-way migration in 3D. Uh, and one-way migration is superior to ray-based migration in multipathing cross, for example, around salt bodies. And one-way is sufficient if there is a non-steep dipping reflectors. So for the two-way wave equation migration, it's more accurate when it comes to dealing complex structures compared to one way, and it will produce a more focused image for a better interpretation. And derived by minimized least square error into iterative migration. An artifact with low frequency can be produced from a diving wave created. Artifact can be reduced by improving amplitude preserved migration when using a two-way wave equation migration, and it's also great in dealing with steeper dips reflectors. So as I mentioned before, the two-way migration is greater in handling steep dipping areas, and as presented by Mulder and Plessis in 2004, the one-way wave equation should provide images that are geometrically the same as the two-way wave equation migration for dip up about to 70-degree dip angle, and is confirmed by the image shown in Figure 1 and Figure 2. It is well known that a one-way wave equation does not provide a correct amplitude as apparent from the figure below, and the one-way wave equation cannot provide a proper image for the 80-degree dip angle. And the evidence can be seen from the figure 3 below. Because of the kinematic errors in the one-way seam, the migration summation is not constructive for this steeply dipping reflector. And the two-way migration, however, correctly image the 80-degree dip angle, although it does not provide a crisp image because of illumination problem and lack of long offset. And this demonstrates the ambiguity is deciding whether the two-way migration is better than one-way migration. And two-way migration can handle steep dip. However, one-way migration may suffice if there are no steep dip in the Earth model, or if the recorded data do not contain events related to steep dips in the model because of acquisition limitation. So the disadvantage of using two-way wave equation migration is the occurrence of the diving waves that later produce the artifacts. And this is where the iterative migration take place to reduce the artifact and also and improve, and also focusing more on the reflectors. So in the figure below, this is a result by Mulder and Plexis in 2004. So on the left side is a one-way migration result from the real data of the Gulf of Mexico, and the middle part is the two-way wave equation migration data that produce the artifacts. And the right side of the figure is the iterative migration. The linearized iterative migration was carried out with a frequency from 6 to 20 Hz at 0.25 Hz increment. So the result after 6 iteration is displayed in the figure above, and the spatial low frequency artifacts are weaker but not have been completely removed. So this recent major advances and discovery was found by Shosong in 2020, where the depth migration based on the two-way wave equation to image OBS multiples have been found. So with the development of the marine seismic exploration, the ocean bottom seismometer, or known as OBS, as a new seismic acquisition technology has been widely concerned. And although the multiple wave are frequently used as the noises, and they may carry a wealth of subsurface information and produce a broader illumination than primary wave. So to perform a multiple wave imaging, they propose to utilize a two-wave equation depth with field exploration method, which is rarely used, and the multiple wave outperform the main wave in imaging, laying the groundwork for practical use. So the proposed method also found that use the laser storage space to compare with the reverse time migration. So this is the comparison of imaging result. So the image result in A is a primary wave, and B is a multiple wave by two-wave equation depth migration method, and C is the imaging result of multiple wave by reverse time migration method. As you can see, it is much more clearer when we're using a two-way wave equation depth migration method. So to conclude, the migration used to image the subsurface features by converting a seismic section wave field into a reflectivity display. And two-way wave equation provide a better result than one way in case of a steeper dipping reflectors. And the cost of the method can reduce based on the objective of the study. As I mentioned before, if there is no steep dipping area, we can use a one-way wave equation migration. So next is to interpret the complex subsurface. The two-way migration is needed since it have a more accurate algorithm to delineate features in that model. So that's all for my presentation today, and thank you for listening and have a good day. Thank you.